I'm Professor Rad, and this is Precalc video 2-3, the Rational Zeros Theorem. In this video, we're going to be talking about the Rational Zeros Theorem, or sometimes called the Rational Root Theorem. So we're going to explore what this theorem is, state what it means, and then we'll do a couple of examples of applying this theorem. The main time you're going to use this theorem is if you have a polynomial that's got integer coefficients and you want to try and factor it, and you're like, I don't even know where to begin. So like think about if you were going to factor the number 385, you might know, okay, well that 5 goes into that because it ends in 5. But if you have 387, you might look at that and say, oh gosh, I don't even know where to begin in factoring that number. How do I do that? So that's what this theorem is going to be useful for, but for polynomials instead of for numbers. So let's take a look at it. If you want to pause the video and copy this down while I'm out of the way, feel free to do so. All right, so the Rational Zeros Theorem, or sometimes called the Rational Roots Theorem, says the following. We're going to let f of x be a polynomial function. Remember, this is what polynomials functions look like. But we're going to specifically be looking at polynomials that have integer coefficients. So that means we're allowed to have something like 2x squared, but we're not allowed to have something like 3/2 x squared, or 2.7, or pi x squared. So we want all our coefficients to be positive and negative whole numbers. If we have a polynomial in that form, then any rational root, so any rational 0 or x-intercept, has to have this format of C over L, where C is a factor of the constant term A0, and L is a factor of the leading term, of the leading coefficient, which is AN. So what this means, this tells us, it gives us a way to know if we're going to break down this polynomial, if we're going to factor it. It gives us a smart way to identify rational potential candidates for zeros for the function. If our function has a complex root, like something involving I, or if it has something involving like pi, so an irrational root, this theorem is not going to help us. So it's not an all the time helpful theorem, but for our purposes, it's going to be helpful pretty much all the time. So I like to use this ratio C over L to help me remember that C is a coefficient of the constant term and L is a coefficient of the leading term. So let's do an example of finding the candidates for rational roots for a polynomial function, and then determining which ones of those candidates are actual zeros. For this example, we need to find the rational roots, or the rational zeros, of P of t, which is t cubed minus t squared minus 7t plus 3. Now, ordinarily, when we go to factor a polynomial, we might start looking for specific forms that we may know. So for example, if I have like x squared minus 9, I know that that's a difference of perfect squares, so I can factor it. If it fits our perfect square form, we can factor that. If it has the form x cubed plus 1, then that's a sum of perfect cubes, and we can factor that using formulas that we may have memorized in the past. In this case, we have a cubic, and we have 4 terms, so none of those techniques are going to apply, and probably grouping is the only way we know how to factor something like this, and grouping won't work because there's no way to rearrange these terms as they are now to be able to get like those common blobs to factor out. So we're in a situation where none of our factoring techniques of the past will be helpful. So we're going to apply the rational zero theorem to help us find roots, to help us break down and continue to factor this polynomial. So to do that, we're going to start by finding our options for C and our options for L. C are factors of the constant term. So our constant term is this 3. So our factors of 3 are 1 and 3. L are the factors of the leading coefficient. So our leading coefficient here is a 1. So our only options here are 1. Next, I guess I should have mentioned before we even began to check all my coefficients, make sure they were integers, which they are, so we're good to go. If they weren't integers, we couldn't apply this theorem. We'd be in big trouble. So, so at any rate, so now that we found our options for C and for L, we want to find all possible combinations of them where C is a numerator and L is a denominator. So I usually like to go with my first one over the denominator, and then however many there are, that'll be my method. So we'll see another example where there's more. But right now we've got 1 over 1, which is 1. And then we also have 3 over 1, which is 3. Now, in this situation, when we talk about factors of the leading term, of the leading coefficient of the constant term, not only could those values be positive, but they can also be negative. So once you've got your positive candidates for your rational zeros, you can just duplicate them, make them negative. So we also have -1 and -3. These are our rational root candidates. This means if this polynomial has a rational zero, it's got to be one of these 4, and that's it. There's no other rational number that's going to be a 0 or a root to this polynomial. So that's our first part, is we found our candidates. Not too bad, only 4 of them for this one. Next, we have to figure out which ones actually are the rational roots. So to do that, we're going to apply theorem 2. That was our equivalent statement theorem. And to figure out if any of these are roots, we can plug them into the function. And if we get 0, it's a root. And if we don't get 0, then it's not a root. So we have to find P of 1, P of 3, P of -1, and P of -3. So I'm just going to zip through and work through those. You can do that as well if you want to check your evaluation skills. But I'm just going to pause this real quick so I can work through them. And then you can pause and work through them too if you want. And we can unpause and then check and see if we get the same values. Alrighty, so here's how I calculated P of 1, 3, -1, and -3. And I found answers of -4, 0, 8, and -12 when I substituted in. So what we're looking for in order to be a rational zero or a rational root is to get 0. So this is the only one that we got 0, which means that 3 is a rational root. So the rational roots of this polynomial are just going to be 3. So the good news is that the rational root theorem, the rational zero theorem, will give us a method for finding some candidates. So we narrow infinite choices down to finite choices, and then we just have to check all of them and see which ones give us 0, and then we can use that to find our rational zeros. So this one, our leading coefficient only had a factor of 1. So let's do an example where our leading coefficient, maybe even our constant term, have more factors. And for that one, we're just going to list the candidates. So we're just going to stop at this point. We're not going to bother to check all of them, just so we get practice applying the theorem to find the candidates. So for this example, we've been asked to list the candidates from least to greatest for the rational roots of this polynomial function f of x equals 6x to the 5th minus 3x squared plus 2x minus 8. So to do this, what I'm going to do first is find the rational candidates, and then at the end, we'll put them in order from least to greatest, as we've been directed to do here. So applying the rational roots theorem, first we're checking all of our coefficients are integers, they're positive and negative whole numbers, so we are good to go. So I need to find all of the C and the L's. So we're going to be looking for C over L. C are factors of the constant term. So I'm going to look at this 8 and think of the factors of 8. So the factors of 8 are 1, 2, 4, and 8. So this is where we're getting C from, factors of 8. And then this is where we're going to get the L values from, factors of 6. So our leading coefficient is 6, and factors of 6 are 1, 3, and 6. Oh, and 2. How did I leave out 2? Goodness. 1, 2, 3, and 6. So this time we have considerably more values for C and L. So that means we're going to have considerably more possible candidates for rational zeros. So to make sure you don't miss any, you want to go through this in some methodical process. This is the methodical process I use. It doesn't have to be the one you use, but you want to make sure that you're not jumping around so you're not missing anything. So what I like to do is I'm going to take this first value for C and I'm going to put it over each of the values for L because our rational candidates have the form C over L. So I'm going to have 1 over 1. Then I have 1 over 2, 1 over 3, and 1 over 6. Then I'm going to move over to my next value of C and repeat. So I'm going to put 2 over each of these. So 2 over 1, 2 over 2, 2 over 3, and then 2 over 6. Then I'm going to move over to my next value of C and repeat. So I'm going to do 4 over each of these. And then I'm going to finish by doing 8 over each of these. So 4 over 1, 4 over 2, 4 over 3, and 4 over 6. Then we have 8 over 1, 8 over 2, 8 over 3, and 8 over 6. Now you'll notice as I made this list, this is what I would call like very like brute force list. It's nothing's in simplest form, like 1 over 1 I could simplify if I wanted to, and I'm going to my next kind of stage of this. But when I'm doing the rational zeros test, I like to make sure that I don't miss anything. So I'm going to make sure and I go through and list all of them in this manner. Then I'm going to go through and I'm going to simplify each of them. So on the board, because I don't have a lot of space, I'm going to erase them. If you want to do that on paper, you can. You can also rewrite a new list, whatever's going to work best for you. So for instance, I'm going to rewrite 1 over 1 as 1, 2 over 1 is 2, 4 over 1 is 4, and 8 over 1 is just an 8. 1/2 is reduced, 2 over 2 is 1, 4 over 2 is 2, and 8 over 2, that's 4. 1/3 is reduced, 2/3 is reduced, 4/3 is reduced, 8/3 is reduced. Nothing I can do there. 1/6, 2/6 is 1/3, 4/6 is 2/3, and 8/6 is 4/3. All right. So now we've gone through and we have reduced each of those fractions. Now, truth be told, I tend to write my fractions in simplest form as I go through that in my first pass. Do what's going to work best for you. If it helps you to write these out in multiple steps, do that. It's not like a race. No one cares how long it takes. You just want to make sure you're doing it accurately, right? So now that we've got this set up, now we're going to get rid of duplicates. So this is now like a second or third pass through this list. So for instance, I notice that I have 1 has repeated, 2 has repeated, 4 is repeated. Let's see, 1/3 has repeated, 2/3 repeated, and 4/3 also repeated. Anything else? I think that's it. I think that that's our list now. So now we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 20 rational zero candidates. How did I get 20? Remember, for every positive candidate you have, you also have the negative form of it. So we have 10 positive rational candidates here. So we're going to have 10 negative as well. So we're going to have, if I want to find all of the rational zeros for this function f of x, I'm going to have to check 20 values, which is better than infinity, but it's still kind of a lot. So for the last part of this, we were told to write these in order from least to greatest. So what I'm going to do is I'm going to list out for myself some spaces to write my answers on. Actually, what I'm going to do is I'm going to rewrite these just off on the side. So I have some space to write my answers, I think. So we had 1, a half, a third, a sixth, 2, 2/3, 4, 4/3, 8, and 8/3. So to write these in order from least to greatest, I'm going to start with the negatives because those are least. But I'm going to think of the amount as the largest number because negatives and positives are mirror images, right? So I'm going to go from the largest number, which is 8, and I'm going to start writing -8. It's my first one. Then I'm going to cross it off the list so I don't repeat it. Then I can already see I'm going to run into a little bit of trouble because I have some improper fractions. So 4/3 is the same as 1 1/3, and 8/3 is the same as 2 2/3. So that's going to help me put those in order. So the next biggest number is 4. So I'm going to list -4. Then we have 2 2/3, so 8/3. So I'm going to have -8/3. Then we have 2. So we're going to have -2. 1 1/3. So we have -4/3 will be next. Then we have 1. And now we have our proper fractions. So 2/3 is the largest of these three. And then we'll have a half, a third, a sixth. So -2/3, -1/2, -1/3, -1/6. So these are our 10 negative rational roots in order so far from least to greatest. And now to put the positive ones in, we're just going to follow the mirror of this. So the next one's going to be 1/6, and then positive 1/3, a half, 2/3, 1 4/3, 2, positive 8/3, 4, and 8. So there we go. So if we were to list all the candidates from least to greatest for the rational roots, for the possible like rational factors of this polynomial, this is where we would get to. Whew, all right, so that concludes this video on the rational zeros theorem. In the next video, we're going to look at a couple of theorems to help us do some more breaking down, some more dividing. So in a previous video, we did an example that that required synthetic division. So we'll do another example with synthetic division. We'll do some long division with polynomials, and we'll see if we can find a way to figure out if two polynomials are going to divide evenly quickly without having to do all that division process. So I look forward to seeing you in the next video. I hope this helped you with the rational zeros theorem, and I look forward to seeing you in the next one. Bye for now.